Hi everybody, I'm going to speak on my master's thesis work at WinLab, and the topic is heterogeneous network testbed integration and wireless network virtualization. So the outline of the presentation is we have integrated the ORBIT lab, the PlanetLab testbeds. So first I'll describe the differences in the two testbeds. Then I'll describe the integration model of the two testbeds. Then I'll move on to wireless network virtualization, the challenges and approaches towards it, and after that I'll show the differences between SDMA and VIP based virtualization schemes. I'll explain the two virtualization schemes in detail, and then some qualitative differences between them after the quantitative differences, and it'll be concluded. So our first topic is the PlanetLab ORBIT testbed integration. So the ORBIT testbed is a wireless testbed integration at WinLab with 400 wireless nodes that allow for sequential access to the grid. So the users have to reserve the grid and one user at a time access. So because of that, we have a control framework, the node handler, node agent, which I'll explain later. Which facilitates easy experimental setup and execution, so that the useful time of experiments is at the grid is spent at the execution of the experiment. Whereas the PlanetLab is a wired testbed which is contains globally distributed set of nodes, and which supports both long-term as well as short-term access to the experiments. So the PlanetLab has a distributed virtualization model, that is, each experiment runs in a so the PlanetLab testbed has a distributed virtualization model. So it supports multiple concurrent experiments together. Each experiment runs in a slice. So slice is a subset of the globally distributed resources. And however, PlanetLab lacks an official experimental control framework like the ORBIT. So our model basically integrates the two testbeds by extending the ORBIT's control framework to the PlanetLab node, so that the ORBIT users have a single experimental interface to conduct integrated wired wireless experiments. So this is the integrated model. So this is the ORBIT side. A user logs into the ORBIT console and provides an experiment script, which is a Ruby script based description of the dynamics of his experiment, and that is passed by the node handler, which runs on the console. And the node handler parses the script and sends commands to node agents that run on every ORBIT node, and sets up the experiment as well as executes it. So we have extended the node agent functionality to work on ORBIT nodes. Prior to the extension, we created long-running ORBIT slices on the PlanetLab nodes. So the ORBIT integrated experiment will work on those slices, and the red and blue show other experiments that might be concurrently running on the PlanetLab nodes. So now I'll describe in detail the model. So when you in an integrated experiment, how do you select the topology? So basically in ORBIT, wireless networks have implicit topology. However, PlanetLab testbed does not support any topology. So what we have done is we have gone with manual addition. So users manually provide the PlanetLab node that they want to add, or they give some metrics like the link or node, and then according to that the PlanetLab nodes are selected. So in PlanetLab experiments, the PlanetLab nodes are accessed through their DNS names directly, whereas in ORBIT we address the ORBIT nodes as 1 to 20, 1 to 20, that is depending on their row and column number on the grid. So what we have done is we have extended the PlanetLab's the ORBIT's addressing scheme to PlanetLab. So we address the PlanetLab nodes as 21, 1 to 20, so that the orbit user gets a feel that, you get the feel of an integrated test bed. The last thing is that we have modified the node handler to communicate with the PlanetLab nodes through TCP unicast. So
can you clarify one thing? So when you select the nodes manually,
right.
Is it possible to set up IP tunnels corresponding to a topology? Is that a part of the framework, or do you just accept whatever connectivity PlanetLab happens to have?
We accept whatever connectivity PlanetLab has, but we can also set up tunnels, but that is not useful in PlanetLab because PlanetLab itself doesn't have custom topology support, so it's more for like WINI.
Yeah, but it's true that there is no resource management, but even establishing a logical topology could be important for some experiment, like you want a star or a mesh or whatever.
Right.
In the wired part.
Right.
So when you just select nodes, they may have some arbitrary routing going on, which is based on discovery or whatever applications are running.
Yeah. Right.
But I guess you can put in
so the problem,
that forces nodes to talk.
That you can do, but the problem is like PlanetLab doesn't give you root access. So forwarding packets is not possible. That's why they got in WINI, so that the users have they made some changes in the kernel, and that's the problem. PlanetLab, the main issue is you don't have root access, so you don't have access to the underlying physical layer to forward packets.
Okay, nor is there any facility that lets you choose an IP tunnel to only one neighbor or some other neighbor.
I don't think so. I think it's only WINI. I think that's why WINI has full any custom topology support. So currently in an orbit experiment, the orbit node handler communicates with the orbit node agents using reliable multicast. However, we have modified the node handler to communicate with the PlanetLab node agents through TCP unicast. So this is done because we cannot assume multicast support throughout the internet. So this is the detailed flowchart for the communication. So the node handler in the orbit opens up a TCP server, and then our main challenge was to get TCP clients switched on the node agents. So we had to, for initial communication, we used PSSH, which is a tool which provides parallel SSH into the nodes to send commands to them to start the TCP client. So now the question arises, why not use PSSH throughout? But we didn't use that because firstly, it's a heavy process. Every time there's a handshake, and second is that PSSH doesn't provide any feedback on the commands. Like, it's very weak. It just says either error or success. But in our case, whenever we send commands, we get full feedbacks indicating the type of failure and all. So getting back to that, so when the TCP clients report back, the node handler actually has a timeout. So in case some nodes fail due to node failure, link failure, it replaces them with other nodes, and this loop is repeated till the desired number of nodes, PlanetLab nodes, report back for the user. And then once this is done, the experiment starts, and the node handler goes ahead and sends commands to the PlanetLab nodes that are part of the experiment execution, and every command has a success or a failure reported back. And after the experiment is done, it even cleans up the PlanetLab slices for fresh experiments.
So when I specify 21 something,
right,
it will pick any random.
Yeah, any random.
You have a preferred list.
We have a list which we display, and then if the normally they pick up a particular DNS which maps to like 21,5. So then if that doesn't report, we replace it, and
if the user wants a long distance versus a short distance
right.
node, how does that process work?
So one is that you don't mind any node. So that way it just replaces with that any other node and gives back the DNS. Otherwise, if he specifies that these are my metrics, then it only knows that it only takes those nodes, and in case one fails, it replaces with one more, only pertaining to those
so
groups.
in your orbit script, is
Right.
there any information that you can put about the quality or distance of the node? You haven't done
That I have not done, but there are there's a tool S-Cube, so which PlanetLab has real-time measurements which are reported every 1 hour or 2
So
hours.
why can't
So
we
that
add
we-
something to the script that queries the PlanetLab tool and then selects
Yeah, that
something
you can do.
matches that?
That you can be done for dynamic. So this is the unified script, experiment script that the user has to provide for an integrated experiment with a topology as shown in the figure. So this part is the orbit script, orbit configuration part. So here it configures the access point, and here it configures the client for the wireless flow. The part added by us was this part for the PlanetLab. So when PL ready waits for the node to report, and which basically is this part of the flowchart till the desired number of nodes report. And once they report, then we have two modules. One is def p install. What that does, it installs softwares and other applications from the PlanetLab repository, which the user needs for his experiment. And after that, we have something called def play applications, which starts user applications for experiment execution on the PlanetLab nodes. And the last module is the PL experiment done. What that does is this part of the thing is that it cleans up the slices for fresh to start new experiments on fresh slices. So this is one experiment we did to show the usefulness of our infrastructure. So what we did is we used two topologies, one with a one hop wired and one hop wireless, and we ran two such experiments, and we streamed video from the PlanetLab nodes to the access point and then over the wireless to its client. And we have bitrate measurements shown here with time. We basically varied the PlanetLab nodes according to the distance. So we used Princeton node, one in Washington when it was loaded, and one in Japan. So you can see when we used Japan, the bitrate actually fell, the value fell, and also its variation increased. And similarly with Jitter also, almost 7 times increase in Jitter. So here we don't concentrate on the measurements as such, but we just show that our framework can be used for integrated wired wireless experiments, which increases the scope of experimentation on orbit.
So clarify for others, how did you measure those things? You used the facility?
So orbit has a infrastructure, a facility called Orbit Measurement Library, where you can record real-time measurements from there. So it basically runs on every orbit node and reports to the central OML running on our console. So that's how I got these measurements from the clients.
Does that mean that OML gets instantiated on PL nodes also?
No, presently PL nodes we don't have support for.
When you give the delay or jitter, how do you account for the wire?
That jitter you can calculate at the receiver only. So
Jitter is.
Yeah.
You didn't have.
no, we don't have delay. We have only jitter and
So
bitrate.
if you wanted absolute delay, what would you put?
Then one thing you can do is right now you can create a custom application here which records the packet, or you can put it in the packet header the time.
For future work, would you recommend that we try to put OML function onto the PL slice? I think
Yeah, I think it's we tried that. I mean, I think we were going to do that, but I think it's pretty easy to port the OML code to
Hard or
easy. I feel.
Yeah, I would think that most of the OML may be specific, but you have to write some measurement items that correspond to a wired node.
Yeah, but I think we have most of them, like the throughput deal.
Yeah.
I think we can. I started on that, but then.
So it may be worthwhile.
Yeah, I think
that completes
the only issue will be like how fast how efficient it is, because on orbit it's still local, so this is like over the internet. So the one thing is again the communication layer you'll have to change.
TCP.
Yeah, same TCP. So now I move on to wireless network virtualization, which we evaluated on the orbit testbed. So wireless virtualization is defined as supporting concurrent experiments at the same time. So the motivation behind that was to support both short-term and long-term experimentations on orbit, which currently only supports short-term sequential access. The main challenges in wireless virtualization is since the wireless channel is a broadcast medium, to provide isolation between the experiments, and by providing isolation between the experiments, you also ensure experiment repeatability. The results are repeatable. And one major challenge is the design of resource manager that assigns and distributes the various resources among the experiments, and continuous monitoring if any experiment does some improper usage. For example, if you assign a particular frequency to an experiment, it might hop frequencies, which is incorrect because you might have other experiments on those frequencies. So there are a lot of approaches towards wireless virtualization, which I'll describe later. So again, the motivation behind wireless virtualization is, one is the integration model that we had. So there will be users who will want to run integrated experiments for a long time. So you might want to fit in an orbit experiment in parallel with the integrated experiment. So you have to have some virtualization schemes. And one more thing was that the orbit testbed faced some excessive usage recently. So we were looking into running allowing multiple users to run experiments concurrently. So the first approach that comes to mind is FDMA, that is mapping different frequencies to orthogonal, or mapping different experiments to orthogonal frequencies so that they don't interfere with each other. In orbit, each node has two wireless interfaces. So one way of doing is mapping each experiment to one interface and giving them orthogonal channels so that they don't interfere. The other method that comes to mind is time division multiplexing, that is putting different experiments on, assigning different experiment different time slots, so they share the wireless interface on time slots. And the third approach is SDMA, where you give different experiments different parts of the grid, and but you have to ensure enough spatial separation between the nodes so that there is no interference between them. So something like out of the transmission range of other experiments. In SDMA it's more of slicing than virtualization, because the experiments are not sharing the physical nodes, they are just sharing the testbed. Why we don't consider FDMA for our study is, one thing, it's not scalable, because for example like 802.11b just has 3 orthogonal channels. So for example, which are 1, 6 and 11. So here you can see that we ran 2 concurrent experiments. One was always running on channel 1, the blue one. The red was switching between 1, 2, 3, 4, 5 and 6, and you can see 1 and 6 are orthogonal. So when 1 and 6 were running, both of them were getting full bandwidth. But as the second experiment was put on 5, 4, 3 and 2, there was a lot of interference. So, And the other thing is, so we have to look at channel conservation schemes, that is the experiment sharing the same channel. So we look at those approaches. For example, the same scenario when we give spatial separation between the experiments, so we can see that at least 1 and has improved with 4 and 5, just because we gave some spatial separation. And TDMA has a very stringent requirement for providing synchronization between the experiments, so that at the same time all the nodes of the same experiment are active. And the other is the time slots that you assign to the experiments. If you give you can't give a very small value to that, because it's too difficult implementing that. And if you give large values, then your experiments will face a lot of delay. Your delay sensitive experiments might suffer. So for that we considered VAP as a solution. So the virtual access point is basically an abstraction of the physical access point that supports multiple ESS IDs. So as you can see in the figure, the same access point can support multiple networks on the same interface. And so what we do in VAP based virtualization is we assume that individual experiments consist of one wireless hop, that is an access point and a client. So this is an FDMA virtualization where I put 4 different individual experiments on 4 orthogonal channels. So that maps onto a virtual access point by mapping each experiment to a different ESS ID, and then they actually share the same channel. So VAP, virtual access point based virtualization, provides channel conservation as well as you save on a node. So before moving on to the VAP benefits of VAP for virtualization, this figure shows how the VAP implementation was done in the MAD Wi-Fi driver. So the VAP functionality operates between the IP and the MAC layer, and it sets up virtual interfaces. Right now MAD Wi-Fi supports a maximum of 4 virtual interfaces, and on the transmission side we have 4 different buffers, and it operates in a round robin fashion, so it's fair. And on the receiver side we have only one buffer which receives the MAC frames and scans for the MAC address, and all the 4 virtual interfaces are given unique MAC addresses. So once it receives a MAC frame, it looks at the MAC address and then puts it on the right IP interface. So what we thought was this extra overhead might add to some performance degradation for the VAP. So first work was to compare the virtual access point with a normal physical access point. So basically we compared this topology, the virtual access point topology, with a normal access point with 4 clients, both with 4 clients, but virtual access point had the 4 clients in 4 different ESS IDs, whereas the access point had only one ESS ID. And so we did it for both uplink traffic, that is traffic from client to access point, as well as access point to client. So we found that there is no difference between access point and virtual access point performance. Now moving on to virtualization. So if you consider VAP based virtualization, so this green bar graph shows the throughput for one hop wireless, that is one access point, one client. So if I'm not virtualizing, I would expect this much throughput if I'm running my experiment. But when I'm doing channel conservation schemes like VAP, so my bandwidth will scale by less than 25%. And obviously, since in the uplink I have the experiments will face CSMA contentions between each other, so there will be some throughput variations in addition. One more thing, one more observation from this graph is that in downlink VAP has the advantage of time scheduled transmissions. So it was found that it's almost 25% of this. So whereas uplink there is drop in throughput due to CSMA contentions. So one issue with uplink might be how scalable the virtual access point is as I increase my clients.
I think that one issue that you haven't addressed yet,
Yeah.
with, what happens is that with variable signal quality, the bit rate will tend to change.
Sure.
That will lead to unfairness among virtual access points. Or it could lead to, so it depends on how well it's implemented. My guess is that the present implementation doesn't do anything about that.
So you're saying
if you had 4 equal streams, right now you have a fairness situation
Right.
where they all have good signal and they're pumping, and I guess this measurement is UDP with slowly increasing rate. But this, how did you obtain the blue line?
Blue is basically access point with
how
one
did you
focal.
measure that you kept increasing the rate steadily to reach the limit, or
No, that's for a fixed physical layer rate of 36 mm.
so you fixed the
Physical layer
but,
is fixed.
but
You are talking about auto layer?
how do you determine that blue dot line?
That's
For
a
any
max. That's a maximum throughput we get for each client, and like it was fair.
But
We took the mean
you
basically.
kept
Yeah.
going up steadily until you found this point. I mean, you have like a curve of offered load versus throughput that
Right.
from,
This is mean value actually.
but that all assumes all of them have equal signal.
Yeah, I mean we were checking that the RSSI receive signal strength at the access point is same for the 4 clients.
So even
Otherwise
more
then
robust experimental framework, people might expect to have auto rate or
Yeah.
control over those parameters. The moment they start doing any cross-layer stuff or
Right.
auto rate, then it's not going to work. So I'm pointing this out just for people who might be interested
Sure.
in doing future work on it.
Sure. Because if
This one currently doesn't assume any uplink coordination, right? This is just because they're all equal and you sort of see
Yeah.
that fairness is being.
because even if one client is far off with respect to other clients, its throughput decreases pretty rapidly. Because there's like one thing is its signal strength is low, and the other thing. So if we keep the physical rates fixed, then it will affect the other experiments also. So, and if you keep it auto rate, then it will its throughput will decrease.
So is
So-
there
so you
some
have-
kind of capture effect?
Yeah, capture is also there in this.
But if this doesn't.
No, this won't have capture because we ensured that all have the same receive signal strength.
Yeah, so how realistic is that when if I run a test bed which is open?
How these results?
Yeah, I mean, these are kind of idealized results.
Right. But the thing is, if you keep them at the same distance, then you get the results consistently. The only thing is if the
No, so in any real world virtualization scenario, somebody wants to share an airport network among 4 operators. If one of the operators' access points are not all that well, it depends on where your subscribers are. So
Right.
you might have a cluster of subscribers which are further away,
right,
then the sharing won't be that equal.
yeah, that is.
But
right.
there are solutions to that. So I'm just pointing out that one has.
But
to-
normally in that scenario, it's even more difficult because you don't have access to the clients. In our testbed, at least we have access to all the
But
nodes.
let's assume for now we have access to the client
Yeah.
and you can.
Then
claim
it's
that
easy,
the
then you can,
client
like-
will be upgraded, but assuming that we have to solve the problem more generally.
So now our second scenario for comparison for virtualization scheme is space division multiplexing. So what we did is the same 4 experiments that we mapped to the same virtual access point. We make it as 4 individual access point clients and we put them on the same channel, but we provide maximum spatial separation between them. And we also decrease the transmission power of the clients to the minimum possible value, so that the interference circles for the experiments decreases. So on orbit, our experiment setup was basically, we took for the virtual access point and its clients were set up in this fashion, and for SDMA we had the same the 4 experiments spread out at the corners of the grid, so that there is maximum spatial separation. The first comparison was with offered load. So the blue line shows the VAP curve, and the SDMA curve is the red line. So when the channel wasn't saturated, both the scenarios gave comparable throughput. But however, when the channel was saturated, the SDMA performance, I think it's wrong, it's the other way. I think it's the other way. This is SDMA. So SDMA gave us a better performance because of capture effect. So capture effect is basically the receiver is able to decode collided MAC packets because of the difference in RSSI values. So since the experiments were placed far apart, so in case there was a collision between the packets of 2 experiments, the receiver of an experiment could decode the packets transmitted from a node of the same experiment, because its received signal strength was much higher than the other packets. And we confirmed this behavior by looking at the MAC retries. So you can see the SDMA MAC retries are much lesser, because even after collision, the packets in SDMA were decoded by the receivers. We also measured the VAP downlink throughput, and we got the performance of VAP in downlink mode was very high. This again was because of the time schedule transmissions when you transmit at downlink, and you can see the MAC retries are almost negligible for VAP downlink, since there's no CSMA contentions. In our further study, we won't consider VAP downlink, since the comparison won't be fair. And we also consider this scenario, in which we place the SDMA scenario without giving spatial separation. So we'll show the effect of giving spatial separation on the performance of SDMA. So here we have the 3 scenarios. So again, this is with packet size. So we vary the packet size of experiments. So again, you can see that the SDMA performs better than the VAP. The SDMA with spatial separation performs better than the virtual access point, and the difference in performance increases with packet size. That is because capture effect is more prominent with larger packet sizes. The other graph shows the same performance difference. It shows just the difference in performance. Till now we were considering UDP comparisons. We also have TCP comparisons for the 3 scenarios. The trend is the same. Again, the SDMA performs better than with spatial separation performs better than the virtual access point, and without the spatial separation, you can see performs poorly because of lack of capture effect. And but the variations in TCP throughput were more than UDP. Because TCP has the TCP ACK packets in the downlink, which result in more contention among the experiments. After throughput, we also have we have also characterized the delay, and for delay we also make a comparison with no virtualization case, that is a single AP, single client wireless hop. So we have measured delay with regard to packet sizes of the experiments. So the black line shows no virtualization case. So the delay increases with packet size. That is because your transmission delay increases with packet size. But if you're using virtualization, then the trend will be like a V-shaped curve. That is because when experiments use smaller packet size, the number of packets are more. We have kept the offered load same, so the number of packets are more. So basically the reason for these delays to be higher is because there is contention with packets from other experiments. So due to contention, because in smaller packets you have more number of packets, so there is more contention, so the delay is higher, and then it reduces as packet size increases. But then again, as you use larger packets, the transmission delays are more prominent than contention. Again, the SDMA performs better than the VAP. The SDMA delays were found to be lesser. That again was accounted because of capture effect.
So your y-axis here is in milliseconds?
Yeah, millisecond.
So how do you measure that level?
This is we used ping basically. So these are round trip delays actually.
So in Linux, you're doing the measurement in Linux.
Yeah.
Is that accurate?
You can get in milliseconds,
What's the
but I took round trip. So if you use one way, then
you have round trip, but
right.
if your timestamp accuracy is 5 milliseconds, then how do you know that this is correct, or you're doing this averaged over many packets?
it's average over many packets. But if it's round trip, then it has to be accurate because he's using the same clock, right? If it's
You are, but it depends on the accuracy of the clock with respect to the packet interrupt times. So,
yeah,
right.
that is.
I mean, there's the OS level issue.
Yeah,
of what's the
but that
accuracy
is
of
not
the
so much of issue. But if you take one way, then you have like accuracy is only some millisecond. This at least provides accuracy
The
in
round trip
microsecond.
with averaging over time,
Yeah.
the variation will even out. Okay, so I think you should point out when you discuss this
Right.
that when you said one is better than the other,
Right.
better or worse is not determined by which has higher throughput,
Right.
but the one which has better delay properties
sure.
and better inter-slice behavior.
Right.
And I think you're going to get to that, but whether something has 10% more throughput
Right,
is
or not.
irrelevant.
Sure.
It's more how nicely partitioned it is.
Sure. So the jitter also follows the same trend as delay for virtualized case. However, for no virtualized case, we found that the jitter decreases with packet size. So this is because we are using round trip jitter. So even if we have a single hop, there is contention. So as the number of the packet size increases, the number of packets in the system decreases. So the contention is less. So that's why the jitter for single hop decreases with packet size.
So for the VAP measurements, everything you did was with the UML implementation?
No, we didn't do
You
any.
didn't
No.
use
UML.
So
That
probably
will,
why you don't get any large
yeah.
additional delays.
Sure, that will make it even higher.
So what is the okay, UML would be needed only when you have one CPU and two radio cards. Right?
Yeah, even in VAP, you might,
That's FDMA.
if you are giving the user access to the VAP, then you need to have some isolation.
So what
So,
would be used?
if using UML, I mean UML will give lot of performance degradation. I think something in the kernel. That's all.
But anyway, right now you're only
No, right now it's
AP
yeah,
and
just
not the
no.
client.
We are only working on the Mac level. So next I move on to inter-experiment interference. So when sharing resources in virtualization, one experiment may affect the performance of other experiments sharing the same resource. So so we define something called as coupling factor, which is defined as the performance difference in non-virtualized case and the virtualized case divided by the non-virtualized case. So this would give a measure of the interference between experiments sharing a resource. And we plot the coupling factor by varying the offered load, packet sizes, and the packet sizes used by the different experiments. So
It also depends on which metric you are using. So the jitter, delay, or throughput.
yeah, we have for throughput and jitter.
Also by using the same formula for coupling.
Yeah, the coupling factor formula remains the same for throughput and jitter. So this is the coupling factor for throughput by we are using the virtual access point to take these measurements, and also we have a virtual access point and SDMA with 4 clients, the same scenario. So we found that the blue lines are when the we take the x-axis, basically we are varying the offered load for the first 3 experiments, and the fourth we plot the coupling factor for different scenarios of the 4th experiment. So when the offered load of the 4th experiment is low, the blue line shows the coupling factor for the first 3 experiments, and we find that the coupling factor is almost 0 till the offered load is 6 Mbps. So once after that it increases linearly because the channel saturates. The red line shows the case with when the offered load of experiment 4 is high. So here the channel saturates at lower values of offered load of the first 3 experiments, and the coupling factor increases at about 5 Mbps. The black lines are when the 4th experiment is running a TCP flow. So TCP flow basically pumps, it was found that it has more coupling on the other experiments than a UDP flow, and that was accounted because TCP pumps traffic at the maximum possible rate, and second is TCP has extra interference due to the TCP ACK flowing in the downlink. Again, we found that the isolation, in terms of isolation, SDMA is superior to the virtual access point. And this was with offered load. Then we also measured it for different packet sizes. So we found that experiments using small packet size have more coupling. So you can see the coupling decreases as we use larger packet sizes. And we took the readings for 2 scenarios. That is when SDMA, the 4th experiment was using a large packet size and the 4th experiment was using a small packet size. So experiments using larger packet sizes will have more effect on other experiments than experiments using a smaller size. And in this graph also you can see that the SDMA performs better than the virtual access point.
Isn't that what load?
The offered load is same throughout. It's at channel saturation. So worst case,
6 meg? Is it 6 megabit per stream?
This is around 10 megabit per stream. So around 40 because
coupling factors are very large here.
yeah, because I think channel is saturated. So
So one lesson from all of this is that you have to use admission control so that keep things below channel saturation.
yeah, that is
If you can do that, then
Sure.
it looks like you can get pretty good isolation. But
sure.
you have to be very careful not to let the traffic bump up into the.
There are other issues also. Like one thing is somehow you have to ensure that all experiments use same packet size, because we found that if 3 experiments using 1000 bytes and even one using 128 bytes, so on wireless that affects the
Because you're running at oversaturation. So if you
if you are not in
if you operate while the
then
curves are important, but once you've determined them, you have
Right.
to make sure you operate in the flat region.
sure,
And if you're in that region, I don't think there's much.
then there's no issue. And one more thing is like obviously if you use so you have to have a way of detecting that channel saturation, because if 1000, if you use 4 clients with 1000 byte packets, saturation reaches at some 24 Mbps, but if one of them switches to 128 Mbps, it falls pretty much because. So
what method would you recommend to keep track of channel saturation?
So there's one, I'll describe in the last 2 slides, something called MAC lumping. So it was found that the MAD Wi-Fi drivers were aggregating MAC packets at channel saturation. So we were thinking of, it's not a, we were thinking of that as like you can keep a sniffer and sniff packets. So in case packets are being lumped, so you can say that this channel there's saturation. Others.
So as far as I understand, the idea would be to be able to assess the condition for channel saturation before admitting a new experiment, right? But probably this cannot be done, so you need to first.
No, I actually have 2 ways of doing that. So
is it something that you measure? You measure the effect?
Yeah, so one is like when you're admitting an experiment, you could first only say that I could provide only this much bandwidth to you, and then you somehow have, like we have a mechanism which can limit the experiment to that rate even if he tries to increase it. So, and the other is you actually detect saturation. So detecting saturation is saturation itself is not defined. So because if
I think what you think that for wireless channel saturation in a wired case, the capacity is whatever 100 meg. You can do a queuing model to make sure it stays below saturation.
Right.
Although they don't do that in PlanetLab, they don't care about any of these issues. But if you want to make sure here, you have to know the dynamic mix of user location, signal quality, packet size, flow rate, TCP, no TCP, all that together determines the achievable capacity. So it's a little trickier if you want, but you can be conservative and just say, let's limit it to 60%
right.
and then it will be okay.
Because what we were facing an issue was that we know values at which the virtual access point reaches or the channel reaches saturation, but that depends on a lot of parameters like packet size, your channel rate, if you're using auto rate or if you're using some particular physical rate. So that's an issue. So here's a plot for coupling factor for jitter. We use the same equation as that for throughput, and so how we measured jitter was we had a video flow for one of the experiments from the client to the access point, and the other 3 experiments were using normal UDP flows, and we varied the offered load of those 3 experiments, the UDP experiments, and we found the coupling factor for jitter for virtualized cases with respect to non-virtualized cases. And the lower 2 graphs show lower 2 lines show the plot for coupling factor for 1 MB when the video we used 2 videos, so one was 1 Mbps and the other was with bitrate 5 Mbps. So the effect on 1 Mbps was obviously lesser than that of 5 Mbps. And another thing that we noticed was that in the no virtualized case, the jitter of the video doesn't depend on your offered on the bit rate of the video, but here due to contention, your jitter increases as you increase the bit rate of the video you are streaming. And again, SDMA has lesser coupling than VAP. After the comparison of VAP and SDMA, it was clear that channel saturation affects the experiments. So we have another proof of concept integrated experiment between PlanetLab and ORBIT, where we use a virtual access point supporting 4 concurrent experiments, and we show the effect one experiment can have on the results of the other experiments. And so we run 3 UDP flows from PlanetLab to 3 clients as part of the first 3 experiments, and the 4th experiment streams a video from PlanetLab to the clients. So this is a scenario where we don't have any policy manager. So we don't have, the first two experiments we increase the offered load gradually from 4 to 6 to 8, and then we observe that initially when the initially here when the offered loads are low, the channel is not saturated, the throughput, the experiments get the entire bandwidth. But as the channel saturates, you can see the black experiment that is actually pumping, whose offered load is constant, is affected. Similar, the other two experiments are also affected, and the video quality of as a part of the fourth experiment degrades. So for this, we recommend to use a policy manager in virtualized test beds. So the policy manager would have two tasks. First is admission control. That is, when you use channel conservation schemes, you have to make a decision whether to allow an experiment to share the same channel depending on the available bandwidth in that channel and also the requirements for that new experiment. And the other important thing is assigning a maximum value of bandwidth to an experiment, and also enforcing that it uses, it should have some mechanism of enforcing that. So in case the experiment tries to exceed its allowed value, it should be able to either limit, it. So we have implemented two types of policy managers. So the dynamic policy manager, what it does is it lets the experiments work their way, and then once it senses channel saturation, it limits the experiments to the values it had assigned. And the other is pre-policy, where the experiments are rate limited to their bandwidth values even before the experiment starts. So the channel never reaches saturation in that case. We implemented this policy manager using click modular router. So a click modular router was developed by MIT folks, and we tested this module with both UDP and TCP flows, and it worked well. And the click elements we used are shown in that block diagram, which we actually loaded in the kernel of the clients. And one thing with this is that right now, like, we have given root access, we give root access to the users of Orbit, so they can work, they are free to do whatever they want. But if we have such schemes for virtualization, then we have to give them restricted access like PlanetLab. So because if they have access, they will have access to these modules also. And the MAC clear lumping I was talking about is we found that the latest MAD Wi-Fi driver was aggregating MAC packets in this fashion. So if it gets two separate MAC packets, it was lumping it into a single MAC frame, and the only overhead found was that it puts an aggregated MAC header for the whole packet. So this was done only in channel saturation. So you can see I varied the offered load, and I found the line graph show the throughput for no lumping and lumping. So you can see there's a difference of around 2.5 Mbps in the throughput, and the bar graph show the MAC frames transmitted per second. So for the lumping case, it becomes half of without lumping. And I also did it with the packet sizes. For different packet sizes, the throughput, and you can see the difference in throughput increases because as the packet size increases, the overhead decreases, the overhead of this MAC header. And I've also plotted the channel utilization for lumping versus no lumping, and you can see most the channel utilization for data increases with lumping. I plotted it for physical rates of 36 Mbps and 54 Mbps. So you see the data utilization has increased, and most of the headers have decreased.
Is this a downlink?
This it does for this is for uplink, but it does it for downlink also.
How does it, how would the uplink work? They're coming from different sources.
So if they all will be saturated, we ensure that all of them are saturated.
You have a symmetric traffic flow or asymmetric in this?
In this case, it's symmetric. All have same upward load.
I don't see how it will work on uplink. Downlink you can pack them together and send a combined packet.
Right.
But uplink each node will send separately.
Yeah, but in uplink also,
Within each node,
if you have
load is very
if you have queuing in your MAC layer, then it will join two. It works like
just
TX
based
hop
on
equal
the
to.
queue.
Yeah.
Queue size based.
Yeah, it's it's like works like TX hop equal to 802.11e. In 802.11e they send two packets, but they send them independently. Here it sends it as one. So after quantitative comparisons, we have some qualitative comparisons between SDMA and VAP. So the first point, that the VAPs are limited to only infrastructure mode, that is if experiments need an access point client based topology, then we can give them the VAPs, but if they want more generic topologies like ad hoc, then we are forced to like
So if
virtualize.
it is like if you virtualize a testbed, if the users want to know detailed statistics like number of transmissions, MAC layer details, then those things will not be accurate.
MAC layer details.
Because of the presence of multiple experiments.
I'm coming. You're talking about the VAP? Yeah. So VAP, like since you're sharing the MAC layer, so you
Even if it's like unsaturated, that will not.
Yeah, sure. In VAP, like even the present driver, it gives you statistics of it gives the statistics of the underlying physical layer. So in case your other experiments are using different parameters, so you can't rely on those results, those MAC results. So in SDMA, one of the disadvantages, you need a considerable amount of spatial separation. So if you have, so its scalability is limited by number of nodes. So if you have large number of nodes, you may not be able to provide enough spatial separation, especially in space constrained testbeds like ORBIT. The last point is like if you are conducting some MAC experiments, so you rely on some MAC results, then VAP will be a bad option, since you are sharing the MAC layer stack of the access point among the different experiments. So that case SDMA would be better. So I'll conclude this talk by, so basically the first part was we integrated the PlanetLab and ORBIT testbeds. So we feel that our design should serve as some key issues in the design of more future heterogeneous testbeds. And also we looked at two channel conservation schemes for wireless virtualization, the SDMA and the VAP. And we did find that space separation, SDMA provides more efficiency, less coupling between the experiments, but eventually it will be the qualitative differences that will matter to map different experiments to the particular scheme. We also looked at the policy manager for controlling inter-experiment interference. And I would like to thank my advisor for giving me this opportunity to work on this project. I would also like to thank Ivan for his guidance, and George and Gautam who have worked with me in this project. So that's